Dream to become the next Sir Isaac Newton or Albert Einstein? Learn calculus from Refath Bari, aka 800 over 800 guy, is teaching calculus this year. Watch his videos.
Alright folks, what's up? This is Refath Bari from Bari Science Lab. Today I'm going to show you another example of the quotient rule, but today I really want to give you an intuition for what it means to take the derivative of a function. So if you remember last time in our previous video, we computed the derivative of this function. This function, as you can see, is the quotient of two polynomials, 3x to the fourth minus 2x cubed over 5x squared plus 3x. Now, remember that to compute the derivative of a quotient of anything, the quotient of two terms, two polynomials, two functions, we have to use the quotient rule, which is this rule right over here, this derivative rule. But you've seen that many times. Today I want to show you a visual intuition for what it means to take the derivative of a quotient. But before we do that, let's try to find the derivative of this quotient. Once again, using our good old quotient rule. So let's take a look. This is the function we're asked to take the derivative of. 5 over x cubed. Now recall that the quotient rule states that if I have a function f of x, which is the quotient of two polynomials, let's call them g of x and h of x, then the derivative of my function f of x is going to be the derivative of the top times the bottom minus the top times the derivative of the bottom, all over bottom squared. And you saw that in my last video. But today I'm going to show you how we can find the tangent line to this function at x equals 1. Okay, so this question is basically saying find the equation of the tangent line at x equals 1 for this function, 5 over x cubed. Right, so how do we do that? Well, remember, to find the equation of the tangent line, we first have to find its slope. To find the slope of any tangent line, we have to take the derivative of this function. And how do we take the derivative of this function? Using the quotient rule. So let's go ahead, let's get started. So, let's label our numerator and denominator. We're being asked to take the derivative of 5, which is my numerator, aka my top function, divided by my denominator, x cubed, which is my bottom function. Right? Are those the colors I used last time? Oh, let's switch this up to remain consistent. So blue's gonna be bottom. So x cubed 5. Okay, so this is my top function and this is my bottom function. So remember, the derivative of this quotient of this function is gonna be the derivative of the top times the bottom minus the top multiplied by the derivative of the bottom. And I divide all of that by bottom square. Bottom square. Okay, let's go ahead and do that. This one's much easier because we don't have a polynomial on the top. We just have a single integer, 5. So, I'm going to replace t by 5 prime, because we're going to take the derivative of 5, multiplied by the bottom function, which is simply x cubed. And from that I will subtract the top function, which is 5, multiplied by the derivative of the bottom function, which is x cubed prime. And all of that will be divided by x cubed squared. X cubed squared. Okay, whoops. Okay, so I've color coded everything so you folks can understand. Okay, so as you can see, this is not a minus sign, whatever. I'm being asked to take the derivative of this function, 5 over x cubed, so that I can find the equation of the tangent line at x equals 1. Now, I've established that 5 is my top, x cubed is my bottom. And I know the quotient rule tells me that the derivative of any quotient is the derivative of the top times the bottom minus the top times the derivative of the bottom over bottom squared. That sounds like a lot, but just look at it and you'll see that it comes to you naturally. And we're going to explore that intuitively and visually very soon. Now, I replaced t by the top function 5, and I replaced b, the bottom function, by x cubed, as you can see. Now, the derivative of any number is simply 0, right? Because think about it. If you have a constant, for example, let's call this c, and you find the equation of the tangent line here, what is there to find? There's nothing changing here. So, because there's nothing changing, the derivative of any constant is simply going to be 0, right? So now all of this we can just erase, right? Okay, now we're left with minus 5 times the derivative of x cubed. Remember, we use the what is it called? The power rule. Pretend that there is an invisible exponent of 1, coefficient of 1 here, and we're going to take this exponent of 3, multiply it by this coefficient of 1, so that we get minus 5 times 3, because 3 times 1 is 3, x, and then my exponent is going to be 1 less than 3, which is 2. Divide all of that. Oh, whoa, no. Not red. Divide all of that by x cubed squared, which is simply x to the 6. Alright, now let's just simplify this, because we're almost done. If we simplify this, we're going to get minus 15 x squared over x to the 6. If you notice, we have x, we can simplify a little bit, right? We have x squared on the numerator, x to the 6 in the denominator. So, we can simplify this because we can reduce the exponent of 2 in both the numerator and denominator. So let's go ahead and do that, right? So you have negative 15 divided by x to the 4th, right? And that is, I can rewrite this as a negative exponent. You see this x to the 4th in the denominator. Well, I can write this simply as negative 15 times x to the negative 4. I can write it this way because this negative tells me that this x to the 4th is going to be under the fraction. Okay, so this is this is the equation that we need to plug in x into to get the slope of the tangent line. So we know that x is equal to 1, so let's plug in 1 over here. So we plug in 1. 1 to the negative 4 is simply 1. And negative 15 times 1 is simply negative 15. So the slope of the tangent line at x equals 1 of this function is negative 15. But we're not done. We were asked to find the equation of the tangent line at x equals 1. So how do we do that? Well, what we can do is use the point-slope formula. The point-slope formula states that y minus 1, 1 equals m times x minus x1. We already know the slope of our tangent line is negative 15. So I can write negative 15 times x minus x1. How can I get x1 and y1? Well, I simply plug in 1. We can simply plug in positive 1 into our original function, 5 over x cubed. If I plug in 1 here, I'll simply get 5, right? So that means if I plug in 1 into this function, 5 over x cubed, I'll simply get 5 from my y value. So that means my x1 is 1 and my y1 is 5. And so the equation of my tangent line at x equals 1 of this function is equal to negative 15x plus 15 plus 5. 15 plus 5 is just 20. And so this is the equation of the tangent line for this function at x equals 1. Now, alright folks, so now let's enter our function over here. So 5 over x cubed. So how do we put cube? 3. Okay, great. So this is how our function looks. As you can see, it has an asymptote at x equals 0. Now, our question was to find the equation of the tangent line of this function at x equals 1, right? And I know that at x equals 1, the function has the point 1 comma 5, right? So I wanted to find the equation of the tangent line at this point. Now, I know my tangent line should, I know my tangent line should look something approximately like this, right? Something that approaches the slope of the function as it gets closer to my x value of 1. So how does my tangent line actually look like? Well, let's go back to our formula. We see that our final answer was negative 15x plus 20. Let's plug that into our graphing calculator. So if I plug in negative 15x plus 20, negative 15x plus, where's the plus sign? Plus 20. Now you can see the beauty of calculus. If I zoom in at x equals 1, you can see the slope of the tangent line approaches the slope of the function at x equals 1, right? Even from far away, you can see that the slope approaches each other, but let's zoom in extremely to, let's zoom in infinitesimally small, right? At this point, you can see that the tangent line almost merges with the function at x equals 1. And so, you can see the power of calculus, because we have just derived, using the quotient rule, the equation of the tangent line to this function at x equals 1. Alright folks, so thank you for watching, and see you next time.
Free Science Lab to fall in love with math and science, especially programming.